impulses from the pulsar PSR B1257 were arriving at Earth at their predicted times. In fact, sometimes they came too early, and other times they came too late. From these variations in the timings, Wauchoizen and Freyl were able to determine that there had to be some bodily mass that was changing the rate of the radio pulses. These bodily objects were coined the term exoplanet. For centuries, scientists, philosophers, and sci-fi writers put forward the idea that the stars in the night sky were just like ours, and that they also had planets orbiting around them. In 1584, Italian philosopher Giordano Bruno said, "This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own." In the 1930s, Edward Elmer Smith conceptualized the idea of civilizations on planets orbiting other stars in his novel series, the Lensman series. Yet none of these people were ever able to provide concrete evidence that these extrasolar objects existed. Since 1992, however, we have discovered over 6,000 exoplanets that are either orbiting other stars or freely floating through the black void that is space. This video was originally going to be about the general topic of exoplanets, but while researching for this video, I found it absolutely insane how it took us hundreds of years to discover the first exoplanet and less than 40 years to find 6,000 more. It led me down a spiral of learning the methods by which we have found so many. And while I was researching, two methods came out as being the most used methods. As you can see from this bar graph, which shows how many exoplanets each method has discovered per year, there is a lot of red and green. Those colors represent the radial velocity method and the transit photometry method, respectively. Other methods like the microlensing and direct imaging are used, but are evidently not as effective. So I want to take a bit of a deep dive into how these methods work. So the first one is the radial velocity method, and it fundamentally takes advantage of the wobble of a star. Now, a star doesn't wobble in the conventional sense, that being a side-to-side motion. To understand the concept of this wobble, I want you guys to consider an empty universe with two objects with equal mass. What would happen is these two objects, provided that they already had an initial velocity, would eventually meet each other, but instead of crashing into each other, they would orbit around each other in eternal freefall. Now imagine that one of those objects was significantly larger than the other. In this case, although one of the masses is a lot bigger, the same thing would happen, assuming that they already had enough of an initial velocity. They would eventually orbit around each other and never crash. But the point, or the barycenter at which these two objects orbit each other, would not be dead in the center as it would be in a system with two equal masses. The barycenter, depending on the difference in mass between the objects, would be somewhere closer to the larger mass rather than the smaller mass. Oh yeah, and by the way, the barycenter is basically just the center of mass of the system. This kind of phenomena occurs in planetary systems, where the planet causes its star to move around a point that is not at the star center. However, astronomers can't just directly image the wobble of a star. The side-to-side motion is way too small for direct imaging to produce any meaningful results. Instead, astronomers take advantage of the Doppler effect. The Doppler effect is a phenomena that occurs when the observer observes a change in frequency of the wave due to the source moving relative to the observer. In simple terms that everyone else can understand, imagine you are in a really strong windstorm that is moving due south. If you start moving north, you would notice that the wind is a lot stronger than if you were to just stand still. This is because the air has to travel a smaller distance in order to hit you. If you start moving with the wind, you will notice that the wind becomes weaker as you move forward, because as you move forward, the wind has to travel that extra distance to hit you. This is kind of how the Doppler effect works. And remember, this is all because astronomers can't just see these tiny orbital motions. They have they have to measure all of this through indirectly through light, and every star produces a spectrum with a very sharp absorption lines at known wavelengths. And to explain why they create these absorption lines is because every element on the periodic table basically every element has like if you shine light through a substance made of purely that element, it will create absorption lines that are unique for each of those elements. So if the star moves towards us in its small orbit around the barycenter, those lines shift slightly towards the shorter wavelengths, and this is known as a blue shift. If the star moves away from us, they shift towards longer wavelengths, and this is known as a red shift. These periodic Doppler shifts trace the star's motion along our line of sight. And since a star can only move like this if something massive is gravitationally tugging on it, the presence of a planet becomes basically unmistakable. By measuring the size and timing of these shifts, astronomers can even estimate the planet's mass and orbital period. However, there are some pretty big issues with this method. As stated previously, the radial velocity method relies on the gravitational influence of a planet on its host star. That means, in order to create an observable effect on the star, the planet has to be large enough to create the gravitational influence. And this entire time, I've also just been acting like the star is a perfectly spherical ball of plasma. That is just not the case. A star can have all sorts of stellar activity that may mimic an exoplanet, which could lead to all sorts of false positives and incorrect data. Now, the second method I would like to talk about for today is actually able to avoid these problems relatively well. Transit photometry, as it's called, uses the luminosity of a star to determine whether there is an exoplanet. Simply put, if an object comes between us and the star, then we should be able to observe a dip in its luminosity. Compared to the radial velocity method, this is far simpler. The radial velocity method needs a long exposure time in order to detect the wobble, because you have to see the planet orbiting around the whole star and ensure that you're actually seeing a star wobble. Whereas the transit method only needs a dip in the brightness. And because of the simplicity, astronomers have been able to rapidly increase the scale of exoplanet detection. In 2009, just 17 years after the first exoplanet was discovered, NASA launched the Kepler Space Telescope, which had the goal of finding as many exoplanets as possible. Over the course of its 9-year mission, it discovered 2,784 exoplanets using the transit method. In 2018, the TESS telescope launched and replaced Kepler. The TESS mission is still ongoing, and hundreds of exoplanets have been confirmed, and thousands more are potential candidates. Now, although the vast majority of exoplanets have been discovered through the transit method, it has major drawbacks. First and foremost, in order for the transit method to work in the first place, the plane at which the planet orbits its star must be perfectly aligned with the observer. Basically, what that just means is the way fundamentally the transit method works is you have the observer perfectly aligned with the plane at which the planet orbits its star. But if the observer, let's say, is not aligned perfectly with that plane, then the luminosity dip is going to be so small, significantly smaller, or just totally negligible. And even if the orbital plane is perfectly aligned, the probability of a transit occurring is equal to the radius of the star divided by the semi-major axis of the planet's orbit. This means the transit method has a very strong bias towards planets with shorter orbital periods. And that's because what the semi-major axis basically is since a planet's orbit isn't actually a perfect circle, it's an ellipse. So the semi-major axis just means the point at which the planet is furthest away from the sun. So the further the planet is away from the star, um, the less likely a transit might occur. And another very big disadvantage to this method is the huge percentage of false positives. I think I remember reading that it was like 40% of potential candidates were just false positives. And as stated previously, stars are not perfectly spherical balls of plasma. There can be all sorts of stellar activity that occurs, which can therefore influence the brightness of a star. Um, I remember, like, I think it was either 2020 or 2021. We were starting to see like dips in brightness in the star Betelgeuse, um, and everyone was starting to like speculate that, like, I don't know, maybe it was gonna go like supernova or something, and it would be this beautiful spectacle in the sky. But then we all just realized, wait a minute, it's actually just it's actually just stellar activity that's causing the dip in brightness. Um, so yeah, that's an example, because the method is so simple that it's also simple enough to just be mistaken. Um, and in fact, while the transit method is good for bringing in potential exoplanet candidates because it's so simple, the radial velocity method is also used to confirm their existence. That's why we actually have thousands and thousands of. I think currently the TESS telescope has, I think, 7,000 potential exoplanet candidates, um, whereas we actually have only confirmed about 600. Um, so confirming them is actually takes the longest amount of time. Um, and right now, I'm by no means trying to dunk on either of these methods, because even with all of these limitations, these two methods have completely reshaped our understanding of the universe. I mean, just like a few decades ago, people were just like sitting around thinking that we were the special ones um, with the only star system in the universe with planets orbiting around us. And the radial velocity method allows us to track how a star moves in response to its planets, while a transit photometry method shows how the brightness of the star can change over time. And when you put these two together, you get a far more complete picture than either one can provide on its own. That combination is the reason the number of known exoplanets has skyrocketed over the past few decades. What used to be speculation is now just a catalog of thousands of worlds, each with its own orbit, size, and history.